Good day, everyone. Keji here. So as promised, we're going to review discrete probability distribution. But right now, we are just going to focus binomial and Poisson distribution because that is relevant to most of you. I'll go ahead and share my screen first. Hold on. Let's go ahead and talk about binomial experiment or binomial probability distribution first and its characteristics. The characteristics of a binomial experiment is that a binomial experiment has fixed number of trials. This means that the number of observation, which is n, is known. Second is the trials are independent. This means that the outcome of the first trial does not affect the outcome of the succeeding trials. Next is each trial has two possible outcomes, either success or fail. And then lastly, the probability of success is consistent on every trial. Let's have an example on binomial probability distribution. And then the formula for binomial probability distribution is flashed here on the screen. The problem is Keji decided to guess on the remaining 10 items of the multiple choice examination because he is running out of time. Each problem has 5 choices. So what is the probability that Keji will get 3 or exactly 3 of the questions correctly? This is a classic example of binomial probability problem because we are given a fixed number of trial or observation in the problem, which is 10 items. And then the trials are also independent with each other because each item will have a different question. And then your probability in getting a correct answer on each item are the same because each item has has 5 choices. And then the trials are also identical. So it's a multiple choice with 5 choices all throughout. And then there are only 2 possible outcomes, either correct or wrong. Let's go ahead and define what the given values are in this problem. So our n here is 10. Keji will guess the answer 10 times. And then our x here, what's being asked in the problem is 3. We want to know the probability that Keji succeeds in answering 3 questions. Succeed correctly. It's redundant. So anyway, our probability of success is 1/5 or 0.20 because each problem has 5 choices. This also means that Keji's chance in getting a correct answer on each item is 1/5 or 0.2. Therefore, our probability of failure is simply 1 minus the probability of success, which is equal to 0.8. If we are going to substitute the values n, x, p, and q to our formula, we should arrive on the answer 0.2013. Therefore, Keji has 20.13 chance of getting 3 correct answers by guessing on the remaining 10 items of the exam. Let's have another example of binomial probability distribution. Bits are sent over a communications channel in packets of 12. If the probability of a bit being corrupted over this channel is 0.1 and such errors are independent with each other, what is the probability that no more than 2 bits in a packet are corrupted? This is an example of how we are going to apply binomial probability analysis or distribution in the field of engineering. In this problem, this is specifically designed for maybe electronics and communications engineering, or maybe computer engineering or computer engineers. Anyway, going back to the problem, let's go ahead and define what the given values are. Our n here is 12. This is the total packets of bits sent in the comms channel. And then our x here, what's being asked in the problem is no more than, so it's less than or equal to 2. We want to know the probability that no more than 2 bits are corrupted. And then our probability of success here is 0.10 because based on the problem, it's also given the probability that error or the bits will be corrupted is 0.1. Therefore, our probability of failure is simply 1 minus 0.10, which is equal to 0.90. And then this is an example of a probability that has several distinct values. And then if you are dealing with less than or equal to the symbol, we are going to add the probabilities from 0 until 2 or until the x or k. If you are going to get the probability of 0, substituting the values through the formula, we'll get 0.2820 and so on until probability of 2. After that, you're going to add the probabilities from 0 to 2. Therefore, there's an 88.90% chance that no more than 2 bits in the packets are corrupted. Okay, I hope it's clear. Let's go ahead and review Poisson experiment. I know that we have provided several characteristics on Poisson distribution, but let's just highlight 3 of which. First is events occur randomly and independently of one another. And then second, a specific interval or region by which an event would occur is known. And then instead of probabilities, the average number that the event occurs is given instead. So in summary of the characteristics, the Poisson distribution deals with a frequency with which the event occurs with a specific interval. And then instead of the probability of an event, the Poisson distribution requires knowing how often it occurs for a specific time or distance. So let's have an example. The students in engineering data analysis class usually ask a total of 4 questions per day. What is the probability that no one will ask a question tomorrow? So this is a classic example of Poisson distribution problem. We are given the average number of times an event will occur in a specific period of time. And the average number of time that the event will occur is denoted by the symbol lambda. This symbol here, lambda. So we are going to define the given values in the problem. So our lambda here is 4. Based on the problem, the term usually is used and usually is normally an indication of average value. So 4 questions is asked per day by the students, or a total of 4 questions. An average of a total average of 4 questions is asked per day. And then our x here, what's being asked is 0, because we want to know the probability that no or 0 students will ask tomorrow. We just have to substitute the value for lambda and x in our formula. A here is the Euler's number. We have a constant value for this one. So e raised to the power of -4 times 4 raised to the power of 0 divided by 0 factorial. Our result should be 0.0183. Therefore, the probability that no one will ask a question in engineering data analysis class is 1.83%. Let's have another example. Vehicles arrive at an intersection randomly and independently and at an average rate of 360 vehicles per hour. The traffic lights at the intersection go through a complete cycle in 40 seconds. And then during the green light, only 7 vehicles can pass through the intersection. Now, what is the probability that fewer than 3 vehicles arrive during one cycle? This problem is an example of an engineering problem that somehow some of you can relate, especially CEs and IEs. In this problem, we are asked for the probability that fewer than 3 vehicles arrive during one cycle. So let's go ahead and define what the given values are. So our x here is less than 3 vehicles in 40 seconds. And then 40 seconds here is defined as one cycle. We want to know the probability that less than 3 vehicles will pass through the intersection in one cycle. And what's tricky here is actually our value of lambda. We are given an average rate of 360 vehicles per hour. And in Poisson problems, we should always take note that the unit of lambda must be equal to the unit of the event, which is x or k. And in this case, vehicles per hour is not the same or does not have the same unit with our x, because our X is vehicles in 40 seconds. So we need to convert 360 vehicles per hour to vehicles per 40 seconds. So again, our lambda here is per 1 hour. So we must convert this to per 40 seconds. 360 vehicles per hour is equivalent to 6 hours or 6 vehicles per minute. And then each minute contains 60 seconds. So therefore, in 40 seconds, 4 vehicles pass in the intersection in average. So in 10 seconds, there are 1 vehicle. In 20 seconds, 2 vehicles will pass. 30 seconds, 3 vehicles will pass. And then in 40 seconds, 4 vehicles will pass. Therefore, our lambda here should be 4 vehicles per 40 seconds. And this is also an example of a probability with several distinct values. We have an inequality fewer than or less than 3. So we need to add the probabilities of 0 vehicles, 1 vehicle, 0 vehicles, 0 vehicle, 1 vehicle, and 2 vehicle will pass through the intersection. So we are going to substitute the value if you're given x is equals to 0 plus if our x is equal to 1, and then plus if our x is equal to 2, and then getting the sum of the probabilities, we will get 0.2381. Therefore, the probability that less than 3 vehicles will pass in the intersection in one cycle is 23.81%. Okay, I guess this wraps up our review for discrete probability distribution. I hope you learned something from my discussion, or somehow you are illuminated with the discussion on discrete probability distribution. Thanks for watching and have a wonderful day.